All right, ladies and gentlemen, let's take a look at some examples for classifying discontinuities. You can see here that we have two graphs set up already. In the first graph, we have all three different types of discontinuities. We have a vertical asymptote here, which shows a non-removable discontinuity. Right? It's not removable, so we call it non-removable. We're going to approach infinity on either side of this asymptote, which is kind of what makes that a vertical asymptote, right? That we approach infinity or negative infinity on either side. Here in the middle, that would be about 1, 2, 3, 4, about x equals 4. We have a hole. Notice that the limit from the left and the limit from the right are equal to each other. That makes that a hole or a removable discontinuity. And then here at 5, 6, at x equals 6, we have a jump discontinuity where the limit from the left and the limit from the right are not equal, but we're not headed towards infinity like we were over here around the asymptote. So again, we have a hole or removable discontinuity here at 4, but then non-removable discontinuities at 2, 1, 2, and at 6, this being a vertical asymptote more specifically, and then here at 6 we have our jump. In our second graph, you can see it's very similar. We have a vertical asymptote again. This time we're just going to infinity on either side. So even though as we approach x equals 2, our limit would be infinity, we still have a non-removable discontinuity, right, at that vertical asymptote. That's not a continuous point on this graph. At 1, 2, 3, 4, at x equals 4, we have another hole. And we could even make this kind of filled in. Maybe we want to throw a point out there. This is still a hole in the graph. And then a jump discontinuity again at x equals 6, even though, once again, we have sort of a filled in spot there where the output at x equals 6 would be a value of y equals 1, we still have a jump discontinuity going on. So there's just a little graphical sense of what those different discontinuities look like. Again, we have non-removable discontinuities where we have asymptotes or jumps, and removable discontinuities at the holes. So the question then is, what does this look like from a function perspective? Or if we look at these equations, these rules, what's this going to look like for us? So I have some examples to go through. The first one I already have written out. It's f of x equals x squared minus x minus 6 over x squared minus 4. The way that this is written here doesn't really do us a lot, doesn't give us a lot of information. So I'm going to rewrite this in the factored form, x minus 3 times x plus 2 in the numerator, and in the denominator, x minus 2 and x plus 2 as my two factors. Bear with me, I'm playing with fire here using my pen, but I wanted to make sure you could see all the work through the video. So here goes nothing. So I'm looking for places where this function is not going to be continuous. So really what I'm looking for is x values that are not going to be in the domain of f of x. And by looking at the denominator, I can see that x equals negative 2 and 2 are really kind of my points of interest here, because really it's not that x can equal negative 2 or 2, it's that x can't equal those two values in this function. Those are going to be places where this function is not continuous. Those are two x values that are not in the domain of f of x. So we need to dive in and take a look at what's going on at these 2 points. So I'm going to start out and take a look at what's going on at x equals negative 2. So what's going on here? Well, if I look back at my factored form, which I'll rewrite here so I can scribble on it, you'll notice that x equals negative 2 makes this factor, the x plus 2 factor, equal to 0. The nice thing here is I have a giant 1, right, as you might have called it back in your algebra days. I have a giant 1, which means I can really rewrite this function as x minus 3 over x minus 2. These two functions, side note, graphically look identical to each other. They are the exact same functions, with the exception that this version has a hole at x equals negative 2. This function would look exactly the same as this one graphically, just without the hole. So cool side note there. If you don't trust me, hop on your graphing calculator, go to Desmos and graph the function and see what's going on there. How do I know that this is a hole here? Well, for one, if I were to look at this function and look at the limit as x approaches 2 from the left of f of x, it would be equal to the limit as x approaches 2 from the right of f of x. Very similar to what I had up here and up here around the two holes. Those two limits are going to be equal to each other. Let's take a look. So let's categorize this, and we make sure we have a hole, aka a removable discontinuity at x equals -2. Okay, so let's take a look at what's going on at x equals 2 then. So I'll bring my function down once more, rewritten in my factored form. So now at x equals 2, it's going to make this factor on the left equal 0 at x equals 2. So I really need to see what's going on at x equals 2 from the left and from the right. That seems to give me a lot of really good information. So let's start out and take the limit as x equals 2 from the left of f of x. Now, I could use this version that I have here because this was my original function. However, I'm going to use my simplified version because the value here of this giant 1, if you will, it's not really going to affect what's going on in x equals 2 because that really dealt with the whole over at -2. So I'm going to use the simplified version as I'm doing some calculations here. And in order to calculate this limit, I'm going to set up a little table for myself so I can look at x values and y values as we approach 2 from the left. So x and f of x, set up a little table here. My values I'm going to approach from the left-hand side, so I'm going to look at 0 and 1, 1.5 and 1.9, and we're going to see what's going on as we approach 2 from the left. So at 0, if I put 0 in here, I get -3 over -2, which will bring these down, kind of extend this guy. That's the same thing as a positive 3/2. If I put 1 in, I end up with -2 over -1, which is 2. If I put in 1.5 into my function, I get -1.5 over -0.5, which gives me a positive 3. And if I put 1.9 in, I'm getting closer to 2 from the left. I end up with -1.1 over -0.1, which dividing that gives me an 11. Well, I know that there's not a hole here, and I'm thinking, because when I put 2 into this function, whether you're looking at the original f of x or your simplified f of x, I'm getting some number over 0. And that number over 0 tells me I think there may be a vertical asymptote there. That's my first guess. My first guess is maybe there's a vertical asymptote, but I need to sort of uncover that. Well, when I put 2 in or get closer to 2 from the left, I end up with values that are positive and more positive and more positive and more positive. I bet if I put 1.99 in here, I would get something that's really positive based on what's happening here in this pattern. So I'm thinking that this limit equals infinity. Well, what about the limit as x approaches 2 from the right of this same function? We're going to move a little faster now because you've set up your table before. We'll extend this down so I have some room. Some f of x values. And we need to look at this as to see what's going on from the right. Now, I'm already approaching infinity from the left. If I'm approaching negative infinity or infinity from the right, I'm thinking I'm feeling pretty good here about there being a vertical asymptote, but let's just make sure. As we approach from the right, I'm going to use 4, 3, and 2.1 to start, and let's see what's happening as I come from the right. I put 4 into my function. I end up with 1 over 2. If I put 3 in, I end up with 0 over 1, which is just 0. And if I put 2.1 in, I end up with -0.9 over 0.1, which is -9. So if I look at my values, I start out positive at 1/2, and then I go to 0, and then I'm getting really negative really quick. I bet if I put something even closer, 2.01, something even closer to 2 from the right-hand side, I'm going to get some big negative number. I'm going to go with negative infinity here, which means I have an asymptote at 2 that looks a lot like the asymptote did in our first graph. That's a good result for me, especially because I know what the parent graph of a function like this looks like. I know that a function that looks like 1 over x or 1 over x minus some value, whatever you have in there, 2, 3, 17, 100. These functions have vertical asymptotes, right? This hyperbola has a vertical asymptote. So I'm feeling pretty good about the vertical asymptote, which means that x equals 2, I have a non-removable discontinuity. Also, in this case, more specifically, a vertical asymptote. So there's two examples one example with two different discontinuities, one that deals with the whole and one that deals with the vertical asymptote. Let's take a look at one other example really quickly. And that's if I have g of x equals x, the absolute value of the quantity x minus 3 over x minus 3. And I'm going to look specifically at the point where x can't equal 3, because that's going to make my denominator equal to 0. So this is my problem. This is the value of x that's not in my domain, which means I really want to look at the limit as x approaches 3 of g of x. So when I put that in here, I end up with 0 over 0. Now, this is an interesting point, and be careful. You don't want to write this way. You don't want to write that this limit equals 0 over 0, especially not on your AP test, because that's not what it equals. Right now, we're not sure what this thing equals. This is an indeterminate form. I'm guessing maybe because of this 0 over 0, I'm guessing maybe there's a hole there. That's my first guess, but I'm not really sure yet. I need to do some more investigation. So if this is my AP test, if this is something formal, I'm not going to write this. I have this as my scratch work, and I'm going to cross that out so they know that this doesn't exist. But this is what I want to look at. In order to look at this limit more specifically, I'm not sure what's going on. I'm guessing a hole is happening. I'm going to look to see if the limit as we approach 3 from the left of g of x equals the limit as x approaches 3 from the right of g of x. Because if that's happening, then I have my hole. If not, I go back to my original graph. If I don't have a limit from the left and from the right that are equal to each other, then I'm thinking I probably have some sort of jump discontinuity. So let's very quickly see if we can set up our table. As we approach 3 from the left, my x values and my g of x values, I'll use 1, 2, and 2.5. If I need to get closer to 3 from the left, I will. When I put 1 into this guy, I get 2 over negative 2. When I put 2 in, I get 1 over negative 1. When I put 2.5 in, I get 0.5 over negative 0.5. Well, that's an interesting result. If I simplify this, I get negative 1 here, and I get negative 1 here, and I get negative 1 here, which means this limit from the left is equal to negative 1. Okay, so let's go over here. The limit as x approaches 3 from the right of g of x. Set up my table. X values from the right, we'll use 5, 4, and then 3.5. Putting 5 into my original function, I get 2 over 2. When I put 4 in, I get 1 over 1. When I put 3.5 in, I get 0.5 over 0.5. I get values of 1, 1, and 1. So from the right, it looks like we're approaching 1. This pattern is going to continue if I continue in these tables and I put something in here that's closer to 3 from the right, 3.001. I'm going to get 1 again. That means the limit from the left and the limit from the right are not equal to each other. I end up with a jump discontinuity here. Very specifically, if I take a look at this function from a graphical perspective, I know that x equals 3, 1, 2, 3, we'll label that, is where I have some sort of jump discontinuity. Well, if I label this 1 and label this negative 1 along my y-axis, right, let's be professional and label our axes here. From the right, we're approaching 1. Every value to the right of 3 at 4, 5, 6, they're all at 1. At 3, we're undefined. To the left, any value to the left of 3 either outputs at negative 1 and undefined at 3. This function, this family of functions, is going to have a jump discontinuity at whatever value, in this case, x equal to 3, makes that function undefined. If I give you another h of x, like x minus 5 over the absolute value of the quantity x minus 5, this function is going to have a jump discontinuity at x equals 5. Very quickly, this is going to have 1, 2, 3, 4, 5. At 5, this is going to have a jump discontinuity the same way, right? As I put values bigger than this, bigger than 5 in. 6, 1 over 1. 7, 2 over 2. 8, 3 over 3. Values at 1, values at -1 to the left of 5. And you can test that. The only other example that I would give you right now that's going to have a jump discontinuity is a piecewise function. If I change h of x to equal something like x squared when x is less than 0, or x plus 1 when x is greater than or equal to 0. I have a function I can draw just a quick sketch of what this graph would look like. X squared, I know it's a parabola. We're not defined here, so I have an open circle. We're going this way, and just a simple x plus 1 line when x is greater than 0. This graph of h of x, the limit from the left would be 0. The limit from the right would be 1. The limit from the left doesn't equal the limit from the right. So this, once again, has a jump discontinuity. It's a non-removable jump discontinuity at x equals 0, where this function is not continuous. So there's a few examples. We did a jump discontinuity. We did a vertical asymptote. We did a hole. Hopefully that helps out. Feel free to go back and watch the video again, or certainly ask questions in class if you have them. Thanks.